In this video, I'm going to do an example where we're lucky enough that we happen to know the precision or the standard deviation of all our measurement errors. The new twist is that they're not all the same, they're all different. And that's going to lead to a problem known as weighted least squares. And so I want to set that problem up. So suppose that we have n measurements, and that these measurements are of some unknown mean mu plus some error, and these errors are assumed to be independent and normally distributed, except that they all come from a different normal distribution. So epsilon sub I is normally distributed with mean 0 and variance sigma I squared. And these sigma i's are going to be different for each of the separate measurements. So we can rewrite this formula as, and now we can write down a probability distribution for the epsilons. And because all the errors are independent, I could just multiply the probabilities of each separate error. And we can rewrite this. We can rewrite this expression as follows. Where W is known as a precision matrix. So W is a diagonal matrix with zeros on all the off-diagonal elements, except down the main diagonals we have the reciprocals of all the variances of all the measurements. These quantities are known as precisions, so we sometimes rewrite it this way. So the variance covariance matrix is this one. Where these are the variances of the measurements. The off-diagonal elements of the covariance matrix would be the covariances, but since all the measurements are assumed independent, these off-diagonal elements are all zero, so there are no covariances, so the errors don't covary. And the inverse of this matrix, of course, is the precision matrix. In other words, the precision matrix and the covariance matrix are inverses of each other. Alright, so now I'm going to rewrite this as follows. So this is the joint probability for all the errors. Now, that this is equivalent to that may be not obvious to you, so let me expand it out. So first of all, let's write out what the determinant of W is. And here the determinant is very easy to evaluate because all the off-diagonal elements are 0. So that's going to be equal to 1 over sigma 1 squared times 1 over sigma 2 squared all the way up to 1 over sigma n squared. Which means that the determinant to the 1/2 power is going to be simply 1 over sigma 1 times 1 over sigma 2 and so on all the way up to 1 over sigma n. Now the reason we write it as the determinant is that this formula will generalize to the problem if we had covariances amongst the errors. Then even if these were non-zero, this expression would still be correct. Now this product of the reciprocals, that's what we would expect, because each of these probabilities is going to be a Gaussian and is going to have a prefactor of 1 over root 2 pi times sigma 1. And this one times the prefactor will have a 1 over sigma 2 and so on. So our likelihood function will be constructed from this one. Now the depth of w to the 1/2, as I explained, is these. And now I'm going to evaluate this expression. That's the epsilon transpose. Then we put the w matrix. And then we have the epsilon, the error vector. And we can expand this out. Now we can expand this one. This exponential of a sum is the product of the exponentials. And that is this expression that I wrote down, right? These are all the normal probability distributions for each one. Okay, so with this expression here, written in this more compact form up here, we can write the likelihood function. Right, it's the probability of the data conditioned on the model. So and the error term is simply the data minus the model. And so now we also need a prior. We have just one parameter, mu. Remember the w, the precision, is known. So the posterior is going to be the product of the prior, and the likelihood is going to be proportional to this quantity. Now all that matters is terms that depend on mu, so determinant of w does not depend on mu, so that's just going to be folded into the constant. And so all we're left with is and it's convenient to complete the square on this quantity like we did last time to express it as the sum of two perfect squares. So the most probable value of mu is going to happen when we minimize this quantity here. So let me write this. L of mu is going to be the log of the posterior and now we can take derivative of this with respect to mu. So we can use the product rule. The derivative of this term is just going to be minus 1, so I'll put a plus and a 1 over here. And I also need to do the derivative of, this was the derivative of the second term, multiplied by the first. Now I do the derivative of the first multiplied by the second one. Since it's symmetric, it will be the same expression, and so I can just cancel the 2. And that means that if I set this equal to 0, I can find the best estimate. Mu hat is equal to this divided by this quantity. And it's, I can also, this is a scalar quantity, and so I'm just going to write it as the transpose. It's the usual way it's displayed. This is the weighted least squares formula. All right, let's expand out the top one. So this will be W1 times D1, W2 times D2, so it'll be 1 this becomes, this will just be the sum of these, right? 1 times this plus 1 times this, so this will be, and at the bottom we'll just have the sum of the w's. And so you see the best estimate mu hat is going to be the mean of the data, but now it's going to be a weighted mean, where the weights are given by the reciprocals of the variances of each measurement. So a measurement with a very big variance has a very low precision and is going to be given a small weight, whereas a number with a very small variance has a very high precision and will end up having a very high weight. So it kind of makes sense intuitively. And so the posterior probability will be So let's show that this is actually going to be the case, where I have to complete the square on this quantity. And this is just the sum of the weights. It's just this quantity. So this becomes and this expression right here is this expression, which is just mu hat. So this is equal to and now I can complete the square. And I'm going to ignore this part for now. I'm going to start with this term, mu squared, then this one. And now to complete the square, I have to take the coefficient of mu divided by 2 and square, add and subtract. So that's mu hat squared, and then I subtract minus. And this is a perfect square, so that's equal to. And this part, I could try to complete it, but since it doesn't depend on mu, it's not going to be relevant for the posterior probability for mu. So therefore I just need this quantity, which is the one that appears up here in the posterior probability. So therefore and this is in the form of a Gaussian distribution, and so the standard deviation is the square root of this quantity, or the variance is this quantity. So if I define and so the best estimate is mu is equal to mu hat plus or minus for the error bar sigma, where sigma and mu hat oh, so did I have it wrong before? What did I write? Oh yes, this was wrong over here, right? This should have been with the 1, let me correct it. Just should have been of 1 over the sum of the weights. Or maybe an easier way to remember, which is what I was partly remembering, is 1 over sigma squared is equal to 1 over sigma 1 squared plus 1 over sigma 2 squared plus 1 over sigma n squared. All right, and that completes that estimation problem for the weighted least squares.